My name is Professor O.A. Falaye of the Department of Physics, University of Unilorin. And to demonstrate to you and show you how you conduct an experiment to determine the viscosity of a liquid by Stoke's law. In the first instance, what is Stoke's law? Normally, we know in everyday life we experience drag, we experience tension. For any object that flows or travels through a fluid, it experiences a drag force. And so that is what Stoke's law is out to do. So Stoke's law is a function of the fact that the drag force is directly proportional to the viscosity of the fluid, the radius of the object traveling through the fluid, and the velocity at which the object is traveling through the fluid. In this case, you are talking of the terminal velocity. In other words, constant acceleration. Now, that is that. For this experiment, you have a fluid of unknown viscosity in a cylinder. You have the magnet. You have the micrometer screw gauge. You have the metal bearings of different diameter, and you have the stopwatch. The theory is this: like I said, the purpose of the experiment is to find the viscosity of an unknown fluid by Stoke's law. And so the equation is given like this. If you recall, Stoke's law says that the drag force is directly proportional to the viscosity of the fluid, the radius of the metal ball or bearing falling through the fluid, and the velocity at which that ball is falling through the fluid. That determines the drag force that it will experience. So you now have the Stoke's law given as 4 all over 3 pi a cube rho g is equal to 4 all over 3 pi a cube sigma g plus 6 pi a eta v. Your v is the terminal velocity, eta is the viscosity of the fluid, your sigma is the density of the fluid, your g, as we know, is the acceleration due to gravity, your a is the radius, pi is constant. In this case too, your rho now is the density of the metal ball bearing that is falling through the fluid. So if we know this and we do some rearranging to make eta the surrogate formula, you obtain equation 2, and by further rearrangement you can now make a squared the subject of the formula, which will now dovetail to ensure that you have to plot a squared against 1 all over t, which is expected to give you a straight line graph with intercept passing through the origin. And so if you do that and you plot your graph, you are expected to now have a slope given by net eta v all over 2g rho minus sigma. All of this will has been given to you. If you make your eta the solid formula, since you would have calculated your slope from the graph, you can easily find the viscosity of the unknown fluid. And this is how you go about the experiment. The first thing you do is you determine the diameter of the metal ball. It's your choice. You can either determine the diameter for all the balls at the onset of the experiment, or you determine the diameter one after the other. But in this case, I have chosen to determine the diameter, to measure the diameter from the onset so that I have my record. In the usage of the micrometer screw gauge, which has been demonstrated to us, please let us be careful that once we tighten it using the main handle, you must tighten it up using the ratchet handle, and you're going to hear this sound. Once it starts giving you this sound, that means it's tightened up. You take your reading on the micrometer screw gauge and you can record it. That is the diameter of the ball, the metal bearing. You do the same you loosen it, remove it, take another ball. This one will be D1. Take another ball, again determine the diameter for the next ball. And that's what you're going to do for all of the metal bulb. You can hear the ratchet sound. This means it is tight enough. If you use the main handle to tighten it, you will spoil the micrometer screw gauge. So let us be guided in the usage of the micrometer screw gauge. Now, having done that, you have your magnet here. So the next thing you have to take note of is this. If you drop your ball into the fluid, it will take some moment before that ball attains or assumes terminal velocity. So, which is why you do not start the measurement of your stopwatch from the very top or the end. You allow the ball to drop some distance before you start taking the measurement, which is why our mark, the thread that we have put against this cylinder, is kept some distance away from the top of the cylinder. So what you do is you get your ball, and please take note that in this experiment, you must be conscious enough to avoid error of parallax. You do not stand this way and you say you want to take a measurement. Your eye must be level, must be at the same level with the beginning of the thread. So what you do is you keep the ball close to the wall, and as soon as you drop the ball through the fluid, you allow it to start falling, and you wait until it starts to drop, and you take your measurement. But for this particular one, it is too heavy, and this is telling us that this fluid is not that viscous. Exactly. So let me take a bulb of a smaller diameter. You can see that as soon as it crosses this mark, and as soon as it crosses the end mark, you use your stopwatch, beginning and the end. So you ensure that you take the reading of the time at least twice. On the table, I have it that you should take it 3 times. So one of the things you must ascertain, be sure of, is that you have a fluid that is viscous enough so that you'll be able to see the fall of the ball through the fluid. Now, what is the essence? What is the use of a magnet? You cannot dip your hand into the fluid. The only way you can remove the ball is by placing a magnet against it, and you drag it up. Once you drag it up, it removes the bulbs for you. You can see I've removed this one. I place the magnet again against it, and it helps me. You can see I've removed it using the magnet. You drop it like that on the table, and so you keep repeating the experiment. So for this, in this case, you now have your diameter. You have measured it. Maybe let's take, for instance, you have 20 centimeter. A in this case will be 20 divided by 2, which will be 10. Then you can now have A squared, which will be 100, and you can now have a measurement of your time. You find your average time, and you find 1/T with unit in per second. So you repeat the experiment for different balls of different diameter, and from there you can now have a plot of A squared. You have your graph this way, A squared, which is in centimeter squared, against 1/T, which is in second per second. And so once you have that, you are expected to have a straight line graph which normally should pass through the origin, which is expected to give you a straight line graph with intercept passing through the origin. And so if you do that and you plot your graph, you are expected to now have a slope given by 9 eta v all over 2g rho minus sigma. All of this will has been given to you. If you make your eta the solid formula, since you would have calculated your slope from the graph, you can easily find the viscosity of the unknown fluid. Let me tell you one physical significance of this. You should ask yourself, a practical example is when rain is falling, the diameter of the rain droplet gets big enough and begins to fall through the atmosphere until it attains a terminal velocity. And that is why the rain particle dropping on you, the rain droplet falling on you, is not hurting you as an individual, because it is obeying Stoke's law as a nominal flow, which is small enough but bigger than the molecules or the fluid through which it is flowing. So I think with this you can understand why some liquid are light and some liquid looks heavy. The more heavier a liquid is, the more viscous it is, and you can easily find the viscosity, which is equivalent to the drag force that it exerts on an object flowing through it. Thank you for listening.